Alright guys, here's the last day of your notes for probability. I'm really sorry I couldn't be there, but if you have any questions, please do not hesitate to ask any of the other math teachers. Alright, so on Friday we talked about standard normal distribution, which means when you have an approximately normal set of data that is centered around 0 with a standard deviation of 1, we call that a normal or standard normal distribution. Today we're going to talk about non-standard normal. So what non-standard normal means is that the data is still normal, so it looks approximately symmetric, however it's not centered around 0 anymore and and the standard deviation is no longer 1, which is more typical of what data is. So, first example, let's say you scored a 730 on the math section and the mean and standard deviation for that particular test is 514 and 95 respectively. What would your percentile rank be? Label and sketch this question and use your calculator to find the percentile. So instead of centering this graph at 0, I'm going to put the center at 514. You performed at a 730, which is like way up here, which is awesome. Okay. Again, standard deviation in this case is no longer 1. It's going to be 95. Now, in order to calculate the percentile rank, we want the area of the curve to the left of the value that you got, because that's representing the proportion of people that you scored better than or equal to on the same test. So, in order to find the area, we're going to use normal CDF. And my low bound is going to be negative infinity. High bound or upper bound is going to be 730. Now, instead of 0 and 1, we're going to put 514 for the mean and 95 for the standard deviation. Okay, and this is where we grab our calculators. Okay, so we're going to do second bars, option 2. I already have negative infinity in, so that's good. Or you could just hit negative 9999999, it will do the same thing. Upper bound 730. Now the mean I can change to 514. Standard deviation is 95. And there we go. So I get 0.988. So percentile rank to the nearest percent we'll always assume is 99th percentile. So that means that you scored better than 99% of the people, better than or equal to 99% of the people that took the same test. Remember, a percentile rank tells us the percentage of scores that are at or below the one we got. Okay, let's try another one. On an SAT math test with normally distributed scores, the mean and standard deviation are 514 and 95 respectively, so same as above. Find the probability of randomly selecting a score between these two values. So, if I were to sketch a picture of what I'm going to do here, center is 514, and I'm looking to randomly select a test between 400 and 550. So that would represent the area between those two values. So now this time when I do normal CDF, my low bound is now going to be 400. High bound is 550, or upper bound is 550. Mean is 514. Standard deviation is 95. And that's where I go to my calculator. Okay, so I just got to adjust my bounds here. So 400, 550. Now this happens to be the same info from the last question, so I can just go ahead and paste. And I get 0.532, we'll say. I think it was 5325. So 3 or 4 decimals is sufficient. On your test, I try to give you rounding directions there. Okay, and technically right there, I just chopped it off as opposed to rounding. That'll be fine too. Just make sure you read the directions on your test. Find the percentile rank of somebody who scored less than a 670. So that's going to be very similar to what we did up above, where we found the percentile rank as negative infinity to 670. So my low bound would be negative infinity, upper bound would be 670, and then we're going to do the same mean, same standard deviation. So you'll notice this time I'll just hit negative 99999, like that's a big enough negative number. I'll just change this to 670, go ahead and paste, and I get 0.9497. So again, percentile rank will be the nearest percent, so they're scoring in the 95th percentile. Okay, then as far as getting a score greater than 750, now we're just going in the other direction. So your low bound is 750 this time. Your high bound is going to be infinity. Same mean, same standard deviation. So if I were to sketch what this looks like, okay, here's your center at 515, or excuse me, 514, 750 would be like way up here. And essentially what I'm doing is finding this very small area just to the right of that value. Okay, so my low bound is 750. High bound, I'm just going to hit a bunch of 9s. Okay, same, paste. And 0.0064, so it's very slim chance of getting a score greater than that, which makes sense because 750 is a lot above 514, many standard deviations above. Okay, so 0.0064. We'll say right there. Okay, so let's actually tie that back to how many standard deviations that is away from the mean, just to refresh what we did last week. So I don't ask for this right now, but z-score is how many standard deviations you are from the mean. So it's your score minus the mean, which in this case was a 514, divided by the standard deviation, which was 95. So we're almost 2.5 standard deviations above the mean, which is why it's a very small chance that you're going to even have a test randomly selected that is higher than a 750. And that's just kind of relating it back to our z-score from last week. Okay, so these are all the different types of probabilities I really could ask you based on normal CDF. So in between two bounds, lower and then towards infinity, or as I did in the first example, your percentile rank, which is from negative infinity up into that value. So it's just a matter of knowing the keystrokes in your calculator. Make sure on your test you are showing the calculator work. I do want to see that stuff because that's how I know you're typing things into the calculator right. All right, I'm going to skip example 3. Let's get into this comparison idea. So I've been saying all along that z-scores are used to compare data sets, and that's what we're going to do today. So let's say I have two versions of a standardized test that are given, an April version and a May version. The statistics for the April version, so I write A, April version show a mean of 480 and a standard deviation of 24. The statistics for the May version show a mean of 510 and a standard deviation of 20. Now, technically I used X bar for mean here, but in your calculator it's actually going to be mu. So I'll just go ahead and change that. Mu stands for population standard deviation, but we'll get more into that in our statistics unit. Okay, so Joanne took the April version and scored in the interval of 510 to 540, which I always think is funny to read. It's like, she doesn't tell you exactly what she's got. She's like, I got somewhere between a 510 and 540. And you're like, okay, I wish you would just tell me the exact number, but all right. What is the probability to the nearest 10,000th that a test paper selected at random from the April version, which is the version she took, scored in that same interval? So guys, whenever we're talking about finding the probability of randomly selecting a test, that's finding an area. So in a normal distribution, the center of this data set on the April version was 480, and she scored somewhere between a 510 and a 540. So anytime you're finding area, you're doing normal CDF. Low bound's 510, high bound's 540. Mean on the April version was a 480. Standard deviation's a 24. checking my numbers. It should be good. And there we go. So 0.0094. Wait, 0.0994, excuse me. Okay, it said to the nearest 10,000th. So tenths, hundredths, thousandths, 10,000ths, and I don't think that rounded up. No, it did not. So we're good. Okay, now Maria took the May version, so she took a different test. In what interval must Maria score to claim she scored as well as Joanne? So the whole idea here is that if she's taking a different test, it has a different mean and standard deviation. So in order to claim that she scored as well as Joanne isn't necessarily getting the same score. It's really like landing in the same percentile rank. So she wants to be the same number of standard deviations away from the mean that Joanne was. So the big idea here is she needs to match Joanne's z-scores. And that's how she can claim that she did as well. Okay? So first thing I need to do is figure out what Joanne's z-scores were. So remember, oops, spell Joanne right. Here's Joanne. I'm going to call her first z-score like ZL for Z low, and then I'll call her second one ZH for Z high, because remember, we don't know exactly how she scored. She gave us like a low bound and a high bound. So at the lowest, she said she scored a 510. So that's her score minus the mean of her test divided by the standard deviation. Okay, so that's a 1.25. So 1.25, or now her upper bound was a 540. So at most she scored a 540. Same mean, same standard deviation. So 2.5. So Joanne is scoring anywhere between 1.25 and 2.5 standard deviations above the mean. So now Maria needs to match that. Essentially, I'm just going to take this z-score and say, okay, that's going to be Maria's. But I don't know her score, but I know the mean of her test that she took was a 510, and the standard deviation on her test, because she took it in May, was a 20. So now it's just to cross multiply and solve for x. So I'll do 1.25 times 20. Okay, which would then get rid of the fraction there, so I get 25, and then I just add over the 510. So 535. I'll do the exact same thing for the upper bound here. Okay, so at most, Maria has to score 2.5 standard deviations above the mean. I'll call this y, so I'm not using the same variable twice. Okay, so now I just cross multiply, so 20 times 2.5. Add over the 510. Oops. So 560. So on her test, she needs to score anywhere between a 535 and 560 to say she did as well as Joanne did. And essentially what that would mean is on their reports, they would be falling in the same percentile ranks. So even though Joanne's scores are lower and lower than Maria's scores, they are technically performing equally on two different tests because the difficulty level possibly is different. Like maybe Joanne's test was harder and that's why she scored lower. And then that's why Maria scored better because her test was easier. But comparatively to everybody else who took those same tests, they're falling in the same percentile rank. And that's how we can use z-scores to compare two different data sets. Because it isn't always necessarily what the number is, the grade that you get. It's how did you perform relative to everybody else on that test. And if you're performing in the same percentile rank, that's a better way to compare data, especially between two different tests. Alright, so that's enough about normal CDF. We're going to move on a little bit to something different called inverse norm. And inverse norm does the exact opposite of normal CDF. So normal CDF is used to find area. Inverse norm is when you know the area, but you're using it to find a data value. So finding the data value at certain percentile ranks, we will use inverse norm. We'll enter the area to the left of the value to find the standard deviation. So if you are given the percentile, you're going to know the area under the curve. And again, this is specifically the area to the left. That's important to know. So for example, on a trig test, your mean score was 84 and standard deviation was 3. What score would represent the 90th percentile? So what would you have to get to be able to be like, yeah, I scored better than 90% of people on this test? So essentially what this means is in a normal distribution, here's your center at 84. Okay, and the 90th percentile, well, you got to figure is somewhere way over here. I'll just call it X. I want to know what that data value is. Now, what is the area to the left of the curve? Well, if this is the 90th percentile, that means that that area is 0.9. Because remember, under the curve, 1.0 represents the total area. So what I do is I go to my calculator, and I do second vars. Instead of option 2, we're going to do option 3. It's called inverse norm. Now it's going to prompt you with the area. That's the area to the left of the value you're trying to find, so 0.9. This mean was 84 in this problem, and the standard deviation is 3, so I just plug in what it needs. And I get 87.8. I'll just do that for now. We'll say it to the nearest tenth, because again, on your test I'll be more specific. So that again means that if you were to score the 90th percentile, you had to score at least an 87.8. What about the 50th? Well, 50th is actually pretty easy. 50th percentile means you scored better than or equal to 50% of the people. So you could do the whole inverse norm thing, which I actually should have written out my steps here. I do want to see this. 1 second. Okay, so you could do inverse norm, just like what I did at B, or recognize that if 84 is the center, because that's the mean of your data set, well then you just have to get an 84. So score an 84, and you're going to be at the 50th percentile, because again, that's the center. Okay? What about 30th? So now, that's a horrible curve. So now, we're like way over here. The area to the left of that value is 0.3 because we're scoring at the 30th percentile. So I'm going to do inverse norm. The area is 0.3. Mean and standard deviation are the same, and I just go ahead and plug it in. Okay, so like 82.4. Okay, now if I said you scored in the top, let's say top 20%, so I'm just making this up right now, if you scored in the top 20%, that means the area to the right of you is 0.2. So then if you wanted to know what the value was, remember you're not going to plug in 0.2 because that would represent the 20th percentile. You would plug in 0.8 because it's only ever interested in the area to the left of the value you're trying to find. So just to show you what that would look like, if I do second vars option 3, I'll just change this to 0.8. There you go. That would mean you need an 86.5. Now, if you did 0.2 by accident, it wouldn't make sense because you'd end up with the data value somewhere to the left of 84, and it's like, well, wait a minute. If 84 is the 50% mark, you wouldn't end up being lower than it. You'd want to be higher than it to be in the top 20%. So just keep that in mind. All right, so let's say Lola scored an 82 on that trig test. What's her percentile rank? So now I'm switching it back on you. The center's 84. Lola's here at 82. I'm asking you to find an area. Anytime you're finding, whoops, excuse that. Anytime you're finding an area, that's a normal CDF. So now you have to pay attention. It's not inverse norm. You're going to do normal CDF, negative infinity to 82 means 84, standard deviation is 3. So second var is option 2, upper bound is 82. Standard deviation is 3. Okay, so 0.25. So that means she's in the 25th percentile. If there are 32 students in Lola's class, how many students scored better than her? Okay, so if she's in the 25th percentile, that means 75% scored better than her. So 32 people times 0.75. So 24 students scored better than her. All right, Mrs. Yermis tells her calc class that on the last test, the test scores were normally distributed with an average score of 91 and a standard deviation of 3. Dan tells Steve he scored in the 70th percentile. What was Dan's score on the test to the nearest percent? Okay, so I don't know what his score is, but he gave me his percentile, so that means I can use that area to help find a value. So that's an inverse norm problem. So here's just a visual again of what this looks like. Here's 91%, which represents the 50th percentile, which that's a pretty high score. 70th percentile, we'll say maybe is here. So that means this area to the left of his unknown value is 0.70. So we're going to do inverse norm, 0.7, mean was 81, standard deviation is 3. Oops. So 92.3 or 92.5, which is 93%. Excuse me. Steve's z-score for his test was 1.7. Did he score better or worse than Dan? All right, well, I know that z-score is your score minus the mean divided by the standard deviation. Steve scored a 1.7 as a z-score. I don't know his score, but I do know the mean of the test was a 91 and the standard deviation was a 3. So at this point, I can solve for his score and compare it to Dan's 93%. So I'll do 1.7 times 3. Add the 91. So 96.1. So who did better? Steve did. Steve scored better. And that's because Dan only got a 93%. Now, it doesn't ask this, but what if I asked you for Steve's percentile rank? What I could do is find the area to the left of the curve of 96.1. So now I'm finding the area. So I would do a normal CDF. So second vars, option 2. The low bound would be that. The high bound would then be what Steve's score was, which was a 96.1. Oopsies. Didn't mean to type that there. 96.1. Mean on the test was a 91. Standard deviation was a 3. Okay, so technically he's at like the 96th percentile, so that's why it makes sense that he's performing better than Dan did, because Dan was at the 70th percentile. Now, technically, since I knew Steve's z-score, I didn't have to do it in terms of like 91 and 3. I could have done it in terms of 0 and 1. I could have done second vars option 2. Low bound would still be negative infinity, but then I could change the high bound to 1.7. Mu is 0, standard deviation is 1, and I should get about the same answer. And I do. Okay, so that's in terms of a standard normal distribution when I did it in terms of 0 and 1. But I didn't have to do that. Okay, so the big idea here is to make sure you guys are paying attention to what calculator command you're doing when. So whenever you're doing normal CDF, it's being used to find the area under the curve. And that could be a percentile or any other probability. So typically when we are using normal CDF, it says what is given or known. we would know the mean, we would know the standard deviation, and we'd also know the data value or values that I'd want you to find. So for example, like maybe this is 500, this is 600, this is 400, and I want the area under the curve between 400 and 600 with a standard deviation of, let's say, 100. Okay, that would be a normal CDF because you're finding the area under the curve. Inverse norm is when you know the area and you're finding the data value. And I should say no area to the left. Find data value. So maybe it's asking you the percentile. Maybe it's asking you where is the 80th percentile. So maybe, same idea, the mean on a test is 500 and you want to know what the 80th percentile is. You would know that the area to the left of this value would be 0.8. So you would know still, you would still know the mean, you'd still know the standard deviation, but you'd also know some information about the area under the curve, and that's what you'd use to find the data value. Okay, so that's the end of our notes, and that's the end of our probability unit. Again, I'm sorry I could not be there today, but if you have any questions, please make sure you're utilizing the math office. There are plenty of people that know this content that can help you, so please make sure you ask them. Hopefully I see you guys back tomorrow.